Well, good morning, everybody, and welcome to today's session from Smart Vision Europe. We are looking at usage of SPSS statistics mainly, in healthcare settings. My name's Jarlath Quinn. I'm an analytics consultant with Smart Vision Europe. I'm joined online today by my colleague Rachel, who'll be making sure that everybody's logged in correctly as we're going along. If you haven't joined any of these sessions before, you might want to be aware that they are recorded, so you'll be able to listen to it again afterwards. There's a fair amount of slideware in this session here because we've got some stuff we want to explain and introduce you to certain statistical concepts, etc. So don't be concerned about taking notes or anything like that. We'll email out a link to you after the session's ended so you can download these materials. And if you think it's particularly relevant for colleagues who are unable to join today, it might be possible, if you can get enough of them together, for us to arrange a rerun for them. The best thing to do is just send us an email or drop us a line and just ask us. Otherwise, you can just share the recording with them. And with regard to asking questions, well, all the lines are muted. So we ask you to use the chat panel. And if we run out of time, we'll follow up with you. My colleague Rachel will be monitoring the chat panel as we're going along. I've got quite a lot to get through, so I probably won't be looking at that too much. But if I get a chance, I'll check. Otherwise, please just bear with us. We'll follow up with you offline after the session's ended. And on the same spirit, if you wanted to send us an email or something like that, because a question occurs to you after the session, please do so, and we will take time to give you a thorough answer on that. So if you don't know who Smart Vision Europe are, we are a technology company. We're a gold accredited partner to IBM and also a company called Predictive Solutions and Data Robot. And we specialize in statistics, advanced analytics, machine learning, AI type, data science type technologies and solutions. Though we also work with open source technologies like R and Python and Spark. And we're a relatively small organization. We've got a team of veteran and former employees from the statistical and analytical software industry. We've got 15 to 30 years working in advanced and predictive analytics industry. I've personally started working for SPSS after being a researcher for a few years in 1995 and worked there for a very long time before I joined IBM, and then I worked for a company called SAS Institute, who are also a technology provider, before joining Smart Vision about 10 years ago. So we've been doing this for a while now, coming up on 30 years, well, more than 30 years for myself. And that means we've got quite a lot of experience of applying, statistics and data science and all those types of applications across lots of different sectors, including healthcare and pharmaceuticals and finance and insurance and central government and charity and housing and utilities and manufacturing, etc. So we're very, very well positioned to talk about these types of applications and how they're used. And we've chosen a selection fairly carefully here that we think will address a number of different challenges and a number of different applications that people within the NHS and within healthcare research and healthcare settings more generally typically make use of or are interested in. And we start off looking at things like patient satisfaction. Then we look at interpreting correlations and using that to make sense of how variables are related to each other. Then we're going to jump out and look at decision trees. And we're going to use decision trees to look at satisfaction and model satisfaction, and also to look at health outcomes. So we're going to look at that. Then we're going to look at key driver analysis. Key driver analysis is an application that's actually being developed. It's a tool that's being developed by Smart Vision Europe, and it's something that we provide to our own customers. And that'll be released soon. So we'll be showing you an early release of that. Then we're going to talk about risk statistics, particularly odds ratios and relative risk scores. If you're familiar with statisticians like David Spiegelhalter, he talks a lot about the statistics around risk, and he would mention things like odds ratios and why they're important in relative risk scores. And then at the end, we're going to talk about survival analysis, where we're going to be looking at clinical outcomes for survival analysis and explaining how to apply that in the context around that. So without any further ado, let's have a look at the first application here. We're looking at what we call ordinal data. Ordinal data is rating scales. It means ranked order data. Here we have a data set in SPSS. It's simply measuring patient satisfaction for a clinic. It comes from a site called Kaggle, which is a sort of an analytics competition site where people can take part in competitions to try to predict an outcome with the highest degree of accuracy. So it's free for downloading. You can see that this is made up of scores. They actually range from 1 to 5, where 5 indicates that they're very satisfied, and 1 indicates that they're very dissatisfied, with neutral in the middle. And if we wanted to just do a basic analysis here, we've only got one demographic variable in this data set, but we've got a lot of different things that we're measuring here. So lots of different rating scales. We've got things like, as you can see, overall satisfaction, that's our key outcome. And then we've got like satisfaction of checkup appointment, waiting time, admin procedures, quality of experience of doctors, specialists available, exact diagnosis. So you get the idea. And then we've got something here called patient age group at the end, which we're going to have a quick look at. Bear in mind, this could be anything. This could be a HR survey. It could be looking at, HR satisfaction. It could be looking at patient satisfaction, or anything where we've got some sort of survey with rating scales in it. So just looking at that to begin with, we wanted to say, look at the relationship between overall satisfaction and, say, people's age group, and see if age group or satisfaction varies according to age group. A really typical way to approach that would just be to go down to analyze descriptive statistics and go to crosstabs. Crosstabs are very much the workhorse of SPSS. It's one of the most common ways in which people work with the software. Indeed, the term crosstabs comes from SPSS, the statistics package. It's the command that runs in the background if you're using SPSS syntax. I'm going to put overall satisfaction into the columns. It doesn't really matter but I find it just easier if I put the age group into the rows here. And I'm going to ask it to show me row percentages. And we'll just have a quick look at what the results are. Or if I click OK on that, you can see it gives me this table where you can see very satisfied through to very dissatisfied, and 30 or younger up to 60 or older. And if we look at the very dissatisfied group here, going down through the age groups, we can see that, well, 16.9% of 30 or younger age group are very dissatisfied, compared to 60 or older, where 35.8% are very dissatisfied. Conversely, 25% of those 30 or younger are very satisfied, compared to 11.3% of the 60 or older group. And you might well at this stage start to think that it does look like the older age groups are less satisfied than the younger age groups in terms of their overall satisfaction. At this point, you might be thinking, well, how do I know if this is, to use a dreaded term, statistically significant? We hate this term, but it's a term that is used. Whether this is actually just a random fluctuation that we're seeing within the data. Is it something that, to use a statistical concept, is it something that actually exists in the wider population of patients out there in terms of age group? Are older people in the wider population actually less satisfied than younger people? Well, to find that out, we would run or request a statistical test. We go to statistics here. You can see there's actually a lot of statistical tests that one can request just within crosstabs. There's one that we're going to come back to later on. This is our risk scores. But the most common one that people use is chi-square. And even here, it produces more than one test for us. But if I click OK at that point, it's just going to rerun the analysis. Now we've got a previous crosstab we had up here. Now we've got the crosstab again. And we have a significance value down here of 0.041. That is basically the probability of getting a result as extreme as the one observed, assuming that age group in no way affects satisfaction, that the two things are completely independent of one another. That's our null hypothesis, that age group in no way affects overall satisfaction. And based upon standard conventions, and it is a convention more than a hard rule, we would reject that null hypothesis on here, because this is just marginally lower than 0.05, 0.05 being 5% or 1 in 20, and this is actually coming in closer to 0.041. So it's just beneath that threshold, and we would probably reject the null hypothesis using that that threshold's referred to as an alpha level of 0.05. We would reject the idea that age group is unrelated to overall satisfaction, and we would regard it as, again, to use this awful term, statistically significant. You should bear in mind that you can actually double click on these pieces of output here within the SPSS, and you can actually say, what's this? And it tells you what it is. It says it's a significance level based on the asymptotic distribution. That means an estimated distribution, and effectively, of a test statistic. Typically, a value of less than 0.05 is considered significant. So it'll keep you honest, and if you need reminding of how to interpret that. Okay. What if I wanted to actually graph this or show this as a chart? Well, I'm going to quickly go to charts here and go to chart builder. I'm just going to show you how we might do that. What I would normally do is I would choose something like a stacked bar chart, and I would put patient age group along the bottom, and I would color it by overall satisfaction, which I put in the stack setup here. At this stage, the colors aren't very nice, and it doesn't really scale to 100%. I can edit that so it does so afterwards, or I can actually ask it to do it now, and I do that by getting it to scale to 100% by changing the statistic from count to percentage, and saying set parameters to total for each x-axis. That means horizontal category, total for each age group, basically. Click continue. You can see it. That will scale it to 100%. And then if I don't like the colors, I can change the color. So you can see me change. I could say, oh, that one should be red, that should be orange. This should be like a pale yellow, and that should be, a light green and a dark green. So you can see me doing that. Alternatively, you could go into the templates here and choose some of the pre-specified templates. There's one here for American Psychological Society. Got one here, Bright, Legacy, pastels, that type of stuff. I've actually got one I've created already. You can download these templates off our website. I've got one here called Lollipop, which is specifically for 5-group Lollipop for this type of chart. If I click OK at that point, and then click OK again, you can see it produces this chart here, and it's basically a representation of that crosstab, where we can see that the younger age groups have a higher proportion of very satisfied and a smaller proportion of very dissatisfied than the older age group. We can see it step changing here. The people who are most in the neutral group are really the 31 to 45s, and the people who are most in the dissatisfied as opposed to very dissatisfied is the 46 to 59. A really useful thing to bear in mind is that if you don't like this, if you don't like the type of chart, or you don't like how SPSS renders its charts, you should actually right-click on it, click Copy As, and copy as a Microsoft Graphics object. And if I do that and go to say a Microsoft Office application such as Excel or Word, in this case PowerPoint, I can right-click on here and say paste it as, I can paste it as a picture. Sorry, my mouse has disappeared here. Paste it as a picture, or I could paste it as an object, which let's see if I Control V here. Yes, an object which it understands as a Microsoft Graphics object. So you can see that it's pasting it there as a Microsoft Graphics object. There you go. That's better. Find my mouse cursor again. If I go to chart design, you can see that this is just a formatting that I've used, but in fact, in reality, you could change colors. There's lots of different colors you could use here. So you can create your own chart design. I would probably change the chart type here to stacked again. So I'd make it stacked again. And I could go to quick layout. And like I said, that's quite interesting there. I can see the differences and make it dark in the background. So you can see you can actually, what it's doing is it's pasting the data behind the chart in the background, and it's just rendering the chart, so it allows you to play around with it. Something to bear in mind, most charts in SPSS can be copied and pasted as Microsoft Graphics objects. So if you're putting it into a report or something like that, it's well worth knowing about. Okay, that's that section done. Let's have a look at how we might measure the relationships between these fields. And to talk about that, I want to introduce the concept of correlations. We actually have an entire webinar devoted just to correlations, and we'll be showing you, I'll be providing you with a link to that after this session's ended. So you'll see a little link to all of the different sort of webinars that this session references, if you like. So correlations, if you're not aware of them, just for people who aren't aware of them, are values that run along a scale, and the scale runs from +1, meaning a perfect linear relationship to -1 with 0 in the middle, meaning there's no linear relationship whatsoever. So to put that in context, if I were to show you a scatter plot, this is a scatter plot. It's not of people, it's of cars. We're seeing the relationship here between horsepower and vehicle weight, and it's showing quite a strong value of 0.859. You can see that's quite close to +1, so it's kind of up here. Certainly not random. This next session, this next correlation here is 0.843, sorry, 0.434. It's a weaker correlation as evidenced by the noisier chart. So that's kind of, where is that? That's kind of around about here. Yeah, so it's still positive though. It means that as one value ascends, the other value ascends, that there's a positive relationship. A negative relationship would be something like this. So it'd be horsepower against time to accelerate. You can see that this is a strong negative relationship. -0.7 means that as one value increases, the other decreases. So that might be something like, I don't know, reflex reaction time and alcohol consumption. These would be negatively correlated, whereas things like blood pressure and BMI might be positively correlated. And the closer those values are to +1 or -1, the stronger that correlation is. The closer they are to 0, the weaker that correlation is. Okay, so let's have a look at how we can use correlations when we're working with this type of data here, this rating scale data. Well, if I simply go to Analyze here and go to down to Correlate and down to Bivariate. Bivariate means pairs of variables or pairs of columns. I'm just going to look at overall satisfaction. Let me pick overall satisfaction against something like, let's say, admin procedures. Let's pick that one there. How are these two related to each other? If I click OK at that point, it just gives me the correlation. You can see here, it actually gives me the correlation twice because it shows me overall satisfaction against admin procedures and admin procedures against overall satisfaction. Well, they're identical to one another. The correlation itself is 0.485, so it's not terribly strong, but it is statistically significant in the sense that it's not 0, which is what that significance refers to, and it's based on 452 cases. The diagonals here is just the correlation of the variable against itself, which of course is equal to 1. And it's just not very useful. And for that reason, when we go to bivariate correlation, you can say, show only the lower triangle, because I don't want to see it replaced, and don't show the diagonal. So don't show me the 1. And you click OK at that point. Then it just shows me one cell from that correlation. It makes it much easier to interpret. Now, technically speaking, with rating scales, we shouldn't be using Pearson's. Those are for scale variables, for actual numbers. We should be using either Kendall's Tau B or Spearman, which is just designed for rating scales. Kendall's Tau B can be quite resource intensive. It can take a long time for it to calculate. There's a lot of processing involved in that, as it ranks and rescales the data. So Spearman's is probably the most common one that's used. It's called Spearman's rank order correlation. If I click OK at that point, you can see it's just a little bit less, 0.451, but it's pretty close to it. And if I throw in all of the other variables, so I can say, let's look at all of the other variables. I'll put everything in except age group. Actually, let's put age group in. You'll see that's a kind of contrast. Throw that in, click OK. Now we've got a big table. You can double click on this table and you can say, I want to call up what I call pivot controls here. And I can hide the statistics in layers. So I can put the layers so it just shows me the correlation coefficients rather than the significance values, or the N number, which is the number of cases that we use to calculate it. So correlation coefficient here. You can see there's quite weak correlations here of patient age group. That's why the significance value is so close to 0.05. It wasn't very strong significance value. It's quite a weak correlation, but it's probably not 0. So it's coming out statistically significant in some cases. But if we pick some of the stronger ones here, we can see that there's a strong correlation, let's say, between specialists available and overall satisfaction here, a correlation of 0.6. Quality of experience with doctor, 0.601 against overall satisfaction. In fact, if I go back to it, I can click on this and I can go into what's called style here. And style button appears in lots of SPSS dialog boxes. And you can get it to highlight certain values. So I can say highlight correlations that are greater than, let's say 0.55, just to make it interesting. And that's a bit of a livid color, so we'll change that color from bright yellow, that kind of livid bright yellow, to a paler color. Let's go for something that's just a wee bit not as livid. Click OK, click continue, click OK. I'll click continue and click OK. It'll rerun the procedure here. I can double click on it again, pull up the pivot trays, say just hide the statistics in the layer control here, and I can just see where the main correlations are. And in fact, I can add in, like traffic light, the whole thing. I can add in other colors for, medium size correlations. Most people would regard anything above zero point 0.3 as kind of starting to get interesting in social data. In kind of physics data or scientific data, it's usually above 0.4, 0.5, something up where people start to get kind of think it's interesting. You can actually square these values and find out what percentage of variation one variable explains of the other. I'll be showing you an example of that in a moment. But suffice to say, that's correlations. That's a really useful way for us to actually measure the relationship between one variable and another variable. Now, let me just delete all of that output and we'll move on. We'll just go a little bit further now. We're just moving a little bit further as we explore the relationships between these fields within this data set here, working with decision trees. So working with decision trees means that we can actually start to build profiles of patients or staff or research subjects in terms of some sort of key outcome. So the key outcome could be something like satisfaction, or it could be something like recovery from surgery, or it could be likelihood to be readmitted within 30 days, or some sort of key measure. In doing so, it's finding segments for us. Decision trees find little groups or segments, and they actually also work as predictive models. And they're very popular because they're very visual representations of models, whereas things like logistic regression are quite technical and full of coefficients that require people a high degree of expertise to make sense of. And they're relatively easy to understand. Let's look at an example of one. This is the top of a decision tree. This is just the first bit. Here, what the thing we're pointing out is that decision trees are split targeted outcomes by key factors. The targeted outcome in this case is actually survival on the Titanic. This is a famous data set. 2,201 passengers, 32% survived, 67.7% unfortunately did not survive. This is our baseline. And when we ask the decision tree to find the variable or the factor, which is the greatest discriminator between survival and non-survival, it says it's the sex of the passenger. And it turns out that if there were men, 21% survived. The modal group did not survive. That's why it's shaded here. That forms a group. It's called a node. Also gives it a number 1. And the females, they form node 2. That's group 2. And 73% survived. And it's based on a chi-square test. So it's basically doing a crosstab in the background for you, but it's running all the crosstabs and then hierarchically representing them as a kind of family tree. So it's a very powerful way to represent or model or create profiles. As we see here, if I unfold the entire tree, the algorithm that's running this particular type of shade tree, this particular type of decision tree is called CHAID, and CHAID stands for Chi-square Automatic Interaction Detector, because it's using a chi-square statistic, which is the statistic that we use to compare age group against overall satisfaction. And here we can see, kind of interesting, what it's really good at is it's good at showing exceptions to the rule. So we can see that for the male branch, the 1,731 passengers who are male, it actually uses age to split the data because it says that's statistically significant. And it says male adults were 20% survival rate, male children, 45% survival rate. And then it splits it again by class that they're traveling in. 32% of first-class male passengers, adult male passengers, survived. 8.3% of second class, 16.2% of third class, and 22% of crew. So it's kind of interesting because the group that was least likely to survive were male adult males in second class, who are almost half as likely to survive as third class passengers, something which the movies don't point out. The other thing is that we've got to remember there's actually only 344 women on board, or at least in the data set that we have. So it's nothing like, 50-50 split here. And with women, age isn't included in the decision tree because it's not statistically significant. It didn't make a difference whether or not you were an adult female or a child female. But what it does do is it actually creates, it adds in the class variable again, what class they're traveling in. And very cleverly, it groups together any groups which are not statistically different from one another. So for example, if this was ethnicity or something like that, you might find that certain ethnic groups get grouped together here because their survival chances were the same. If females traveling in first class had a 97% survival, in second class or crew, 87% survival, and third class, 45% survival. So how can we relate that to our data? Well, the thing is that we can actually use this to model things like satisfaction. It doesn't have to be a binary variable. So here's an example of satisfaction using modeling satisfaction, trying to identify when an employee will leave and what factors drive that, where leave within 2 years or remain at least 5 years. And the first factor is attitude of senior staff. That's the thing that's driving that. If we just skip out, and I'll show you how we can apply this to our data set, we're going to go to analyze, down to classify here, and then down to tree. Decision trees is a module within SPSS. It's an optional module. It's usually bundled with say SPSS Professional, I think SPSS Premium. But you can add it, you can bolt it on to SPSS if you don't have it. I'm going to make overall satisfaction my dependent, my target field. That's the thing I'm interested in, just like survival on the Titanic. I'll throw in age group, though I know it won't get chosen. There are more than one algorithms I can use here. Shade is the default one, and I'm going to change the criteria here. That's basically, I'm going to give it the right to create quite small groups, group sizes of 20. That's all I'm doing there. Click continue, click OK. It builds the decision tree for me very quickly in the background. I can double click on it. Something I should bear in mind here. This is actually quite complicated to look at because, as you can see, we've got 5 groups in here. That's hard to interpret. Let me fix that. I'm going to fix that by recoding overall satisfaction down to 3 groups. And I've got a little syntax job here, which is going to do that for me. So I've just got this recode satisfaction to 3 groups. Syntax is just a way for me to record some of the procedures that I've done in SPSS. There's a paste button in SPSS that allows you to paste the command as syntax. So I've just done this earlier. There's overall satisfaction 3 groups. Now I'm going to call up the decision tree again. I'm going to swap these variables around and put in overall satisfaction and run it again. Click OK at this stage. Okay, now I would double click on it. It's a much simpler tree to interpret because we've only got 3 groups within it. So it's something to bear in mind. And if we zoom into it, we can see that the thing that drives satisfaction, the single most important thing, is exact diagnosis. That's the single most important factor here. And it says, look, basically, if they're dissatisfied or worse, that's basically saying dissatisfied or worse, then 81.8% of people are dissatisfied if they're dissatisfied with or worse with their exact diagnosis. But if they're greater than satisfied, so in other words, if they're in a very satisfied group, then 93% are satisfied. So it's a really, really important factor. And then we can look at the groups that split these factors further. So we can say, well, look, if you've got specialists available and that's better than dissatisfied, actually the dissatisfied level drops to 50%. If we look at the people here in the neutral group here, this is neutral. I can actually change how the ranges are shown here. I can say ranges as text, so it says higher than neutral through dissatisfied. So people who are in the satisfied group, basically. It says, well, look, there's these people here are 70% if they're 70% satisfied if they're neutral for exact diagnosis, but that can increase to nearly 90% if they get above neutral in friendly healthcare workers. So that's kind of interesting. They can actually, for this group here, they can just say the healthcare workers are friendly enough, but they're fairly neutral in exact diagnosis. The satisfaction starts to go up at that point. So you can see how this can be used to define the groups and the segments within a number of different factors or a large data set that help drive an outcome. In that spirit, if I just click on this and then very quickly open up another data set, I'm going to open up a different data set here. This is a clinical data set, which I'm going to look at. This is called patient length of stay. It ships with SPSS, this data set. So I've actually got a variable here called surgery result, which I've recoded. And I've actually going to work with a subset of the data, so I can use what's called a variable set. I think I only want to use the decision tree variables. And that will mean some of the variables, some of the fields disappear, makes it smaller. Some of them are hidden now. And it just means when I go to classify decision tree down here, down to tree, I can say, okay, I'm really interested in the surgery outcome, where the outcome is either is either well or other. Other means that they were stable or in critical, or they died during surgery. So I'm really interested in what factors drive that. These are people who've had non-elective admissions. I'm going to say other is the group I'm really interested in here because I'm really interested in people who didn't have the optimal outcome. I'm going to choose all of these other fields related to their lifestyle and related to their treatment, etc. I'm going to click on criteria again. I'm going to allow it to go down to quite a small group size, down to 20 here. Click continue and OK. And we'll look at that decision tree. Let's double click on that. It's kind of I could allow it to go deeper, but I get the idea here. So the first thing it says is surgical treatment. If it's a PTCA treatment, then it's 94% are well. If it's CABG, then 60% are well. And then there's a question about whether or not of that 60% who are well, whether or not they received clot dissolving drugs. If none, then only 40% are well, nearly 60% in the other category. If it was Retaplase or Alteplase, then it's 77% are well. If it's tryptokinase, then it's 56% are well. And then it's about cholesterol, whether that's high or normal. And you can play around with this. So you can say, okay, let's go back and let's take that type of surgery out of it, what the surgery treatment was, and say, let's ignore what the surgery treatment was. What does it look like now? And it double clicks on it. We start to see factors, new factors coming into it. This is okay. Now we're looking at clot dissolving drugs, and we're looking at whether or not they have a history of angina, whether or not they're physically active, which group are in the highest group here in the other category. Well, if I just change this to bar charts, you can see it acts like a sort of filtration. Excuse me, acts like a filtration here. We can see that people who are not physically active, who have had a history of angina and who have received no clot dissolving drugs, quite a large proportion of them are in the non-optimal outcome group and in the other group, etc., etc. So there we're using decision trees, not with a satisfaction or attitudinal data, but we're using it actually with these clinical outcome data. What else can we show you at this stage? Well, there's another procedure here called key driver analysis. This is something which we're going to be releasing in SPSS. It's still in development at the moment. I'm going to show you an example of this, but suffice to say, it's a forthcoming tool from Smart Vision Europe, accessed within SPSS statistics. KDA, as it's called, this is a statistical technique used to determine the relative importance or predictor of variables on a specific outcome. So it creates a ranking for you and tells you, what are the factors which are the strongest drivers of an outcome in the presence of other factors. When you've got other factors, when you've got age, when you've got, gender, when you've got attitude, other satisfaction, when you've got other types of values in there which would help you predict it. So it helps analysts understand what factors influence things like satisfaction, readmission, recovery, service uptake, and the analysis ranks the independent variables in order of the impact that they have upon the target outcome. Now, there are two main measures of Smart Vision's key driver analysis. One is called Shapley values. This is the most robust and most sophisticated. It's actually based on a concept from cooperative game theory and estimates the marginal contribution of each factor to a given outcome. It was actually originally designed to look at players in cooperative games and then work out which players contributed most statistically, if you like, to the particular outcome. It's a very robust procedure, but it's one which is very resource intensive when working with more than 25 independent variables. It does a lot of sort of iterations, a lot of iterations as it swaps them around, takes one variable out, puts another variable in. So for that reason, we've got an alternative measure called relative weight analysis. It's less resource intensive than Shapley values. It's useful when dealing with a large number of independent variables. And in most situations, it will produce very similar estimates to the Shapley method. So let's have a look at that. Let me just clip out and I'll just jump out to that. Let's shut down the patient length, the patient satisfaction data. I'm just going to open up a different data set here, which is patient satisfaction, but measured as scales. So I've just changed them from being ordinal fields. I've changed them to scale fields. You'll see the KDA when it's available. You'll be able to download it and install it yourself if you're a Smart Vision customer. You'll be able to go analyze down to regression because it's kind of associated with regression. You'll see a little procedure here called KDA. And as I say, it's still in development here. I'm not sure if this will run, but I've got a backup here. If I ask for relative weight analysis, yeah, this because it'll run it quickly. It just produces some output for me. I'll open some output which I created earlier. So just say recent used files. Here we go. KDA output, and I'll show you the examples of this. This tells me that the R-square value, R means the correlation has been squared. Okay, so an R-square value of 0.63 means 63% of the variation in overall satisfaction can be predicted using all of these other factors here. And it's actually the square of the correlation. So if a correlation has a square of correlation has a value of 0.4 and you square it, it comes out as 16.16. So 16%. A correlation of a value of 0.5. Of course, if that gets squared, that comes out as 25%. 0.6 comes out as 36%, etc., etc. 0.7 would get you 49%. So this is quite a strong correlation here. It's closer to 0.8 as a correlation. So it's 63% as the R square. It's the proportion of variation and overall satisfaction that can be predicted using these variables. But very important here, the Shapley values have ranked the variables from top to bottom here in terms of their importance. They can be scaled to 100%. So we can say that of the variation that is explained, exact diagnosis accounts for 18% of that variation. That's what's driving 18% of that model, if you like. Friendly healthcare workers, 13%. Specialists available, 12%. Next one down, quality of experience with doctors, 11.9%. Right down to the weakest ones, we're down to 2.5%, 2.6% availability of drugs. So it's really powerful way for us to see what factors are driving it. And what we're going to do is we're going to send that data to when we finish the tool, we're going to automatically export the results out to something like Excel, where people can view these results as charts. If they want to see them as charts, we've got something like a little importance chart here showing exact diagnosis. And we'll also produce what's called a KDA quadrant. This is really useful because it looks at the average satisfaction, that's called performance along the bottom here, against importance. So we can see that actually these are the most important factors here: exact diagnosis, friendly healthcare workers, quality experience of doctor. But they're doing pretty good in terms of their importance. They're above average. They're above on a 2-point on a scale from 1 to 5. They're kind of above this point here, 2.7, which is kind of the midpoint of our range of scales. They're doing pretty good here. Whereas this factor here is actually below average, but it's still quite important. So specialists available. So it's telling you that if you wanted to boost your overall satisfaction, you should work on this area here because it's below performance. It's below the sort of target level of performance. And it's still quite important in terms of its relationship to overall satisfaction. So this is one of the reasons why KDA is quite powerful and quite useful for people to work with. And as I say, this is something which is going to be available to people to download and install into SPSS as soon as we finish developing it in the near future. So watch out for that. You'll see some publicity and some materials coming out from Smart Vision about it. That's called Key Driver Analysis, or KDA. Okay, we're getting down into the last two procedures here. I want to talk about odds ratios and relative risk scores. Why is this important? Well, measures of risk play a crucial role in healthcare for several reasons. One is assessing treatment effects. That means basically measuring the impact of a treatment, whether or not it makes a difference or not, and how much of it makes a difference. Interpreting clinical studies, comparing treatment effects. If you've got two different treatment effects, which one actually which one performs better than another in a single value? Can you actually talk about that in a single value? Public health decision making, things like evaluating vaccination programs. We tend to use relative risk scores and odds ratios to show the impact of vaccination programs. It's a way to make sense of that. And risk communication, it's often a simpler way to communicate complexity, as well as identifying high risk populations. Now, in SPSS, there are two key measures of risk. One is called odds ratio. This is a standard measure which is used throughout healthcare. And the other one's called relative risk ratio. That is also a standard measure. Now, before I show you the results of that, we need to talk about what they are. These are measures of what are called association. So they're not statistical tests in the sense that they give you like a significance value, like the chi-square test. They're actually telling you how much a difference something makes. So that's called a measure of association. And in healthcare applications, these values can indicate if exposure, for example, to a factor increases the risk of an outcome, or conversely can have a protective effect, such as with a vaccination. We can use confidence intervals around them, as you'll see an example of that, to show if the effect is statistically significant. And one type of method is based on calculating odds. That's the odds ratio, or the other one is based on calculating probabilities. That's the relative risk ratio. So again, we have to dig into this and make sure we're clear on what the differences is between odds and probability. If you roll a die and you want to say what's the probability of getting a 3 or a 6, it's 1 over 6. It's nothing to that. It's only 16.7% of occasions you will roll a 6. Odds are not the same. Odds are actually 1 over 5. Because what we're saying is that on average, for every 6 rolls, 5 of them will be a number other than 6. So they're not the same thing. They're slightly different. They're more like, 1 to 5 on is what a bookie might call this, or 5 to 1 against, if you like. If they were trying to bet on it. Odds aren't quite the same as probability. They're related, of course, but they're not calculated in quite the same way. So odds are calculated differently from probability. So the odds ratio is therefore the ratio of the odds. That's the ratio of the odds of A in the presence of B and the odds of A in the absence of B. So A in the presence of B might be, A in the presence, probability of having a lung condition in the presence of smoking versus the probability of having a lung condition in the presence of not being a smoker. It is regarded as more difficult to interpret than relative risk because people don't really think in terms of odds, they think in terms of probabilities. But they're not going away because odds ratios are used, have certain mathematical properties which statisticians and healthcare researchers like. Relative risk ratio is the probability of an outcome in an exposed group compared to the probability of an outcome in an unexposed group. It's a similar thing, except we're looking at probability rather than odds. And in the example we're going to look at the risk associated between smoking and angina. Here, the risk factor is smoking status, whether or not they smoke or not. And angina, of course, is whether or not they have angina or a history of angina. And what we're going to use is we're going to return to the SPSS crosstabs feature, and we're going to click the little risk checkbox button to compute both the relative risk factor and the odds ratio. It actually gives you both by default. You can't cherry pick one over the other. So let's have a look at how that works. If I go back to SPSS here, I'm just going to call up this a data set here, which I've created called odds ratio and relative risk ratio. I'll just go to window here. Just make I got it open. Go to window here. Shut that down. We'll go to analyze here, and we'll go to descriptive statistics and down to crosstabs. And I'll just put smoker. I'm actually using smoker 2. This is a version of this. I'll show you why I've done this in a moment. I'm going to put that in the rows, and I'm going to put angina in the columns. Something that's quite important here is notice the order in which I've calculated this. If they are a smoker, that's the yes group. That's the first group that occurs. If they're a no group, that's the second group that occurs. If they have angina, that's the first group that occurs. Here it happens to be coded as 0. It doesn't really matter. And if they don't have angina, that's the second group that occurs. It happens to be coded as no. And I can look at statistics here and say, look, give me chi-square tests and so forth. I'm not really interested in that moment. What I'm interested in things like is show me the row percentages and switch on the risk statistics down here. Click continue, click OK, and I get this little table that comes out here with risk statistics, and I'll just jump to the output, which shows the same results, but allows me to work through it. So I've highlighted the values here. We can see that, for example, that 68% of smokers have a history of angina in this population, in this group. It doesn't mean it's applying to the general population, just this particular sample. Quite a big sample here, as you can see, of what 10,000 individuals or patients or members of a part of a study. 44.4% of non-smokers have a history of angina. So it's quite a big difference here. Chi-square says this is statistically significant. More importantly, what I've done is I've made sure that the risk factor is in the rows. So I did that deliberately. And the outcome factor is in the columns. And the reason I'm doing this, we actually put a video together on this, is because people find it confusing. If you get them the wrong way round, it divides one variable, one value by another value. And it just kind of assumes that the risk factors in the rows and the outcome, whether or not they have the condition, yes or no, or, is in the columns. But more importantly than that, I've also made sure that yes, whether or not you actually have the condition and whether or not you are in the risk group is also the first value that occurs in both groups. So I've used the recode procedure, which you'll see videos about if you haven't used that before, on our SPSS, on our Smart Vision website, which actually allows you to move or change the order of categories or collapse categories together to recode them. You saw me do that with, for example, run a recode procedure to create satisfaction, get it from 5 groups down to 3 groups. And when I run the analysis on that, what it does is calculating the odds ratio first of all. How is it doing that? Well, it's quite simple, actually. It's looking at the counts here and it's saying, well, let's look at the people who in the yes group, in the smokers, what's the proportion of them who have angina to those who don't have angina? So it's just basically dividing the non-angina subjects or dividing those who have angina by the non-angina subjects. That gives me a ratio value of 2.14. And it does the same thing for the non-smokers. That gives you a value of 0.797. And it takes your ratio of these two values, it gives you a value of 2.69. What does that actually mean? Well, it means that the odds of having angina are 2.69 times greater for smokers than for non-smokers. And this is the point. It's the word times here, which is important. You are 2.69 times greater, a greater risk of having angina if you're a smoker in this population than a non-smoker. And it's times which is important here. So that's how we make sense of odds ratios in that sense. It's the word times. So if it said 0.5, it would mean you are 0.5 times at risk. So it means half as much at risk of having angina than not having angina. If we compare that to the relative risk ratio, we again in both occasions we need to remember these are just measures of association. They're not causal statements. Not saying one thing causes another. They're just saying this is the ratio. If we look at the relative risk ratio, here we're looking at the yes group against the total and the no group against the total. So we're not looking at yes against no's and yeses, but we're looking at the yeses against the total. So here it's saying, okay, I'm going to divide the yes group by the total. Notice that this is exactly the same as the row percentage here, 68.2. See, 0.6822. It's exactly the same. Here, this is exactly the same as the row proportion, 44.4. It just looks at the proportion of one divided by the other here. That gets us a value of 1.538. It says the probability of having angina is 1.54 times greater for smokers than for non-smokers. So probability, not odds. And so it's very important here. Whatever that baseline probability is, you got to bear in mind, this is really important here. The baseline probability is really important. So for example, let's say there was only a 1% chance of you having the condition. Well then, if you're exposed to a certain stimulus and the probability, the relative risk ratio is 1.54 times greater, that means you're looking at the difference between 1% chance versus a 1.54% chance. It's not that big a difference. Whereas if the baseline was 30% chance of having that, then it's 1.5 to 4 times that. So it's like 30% plus 15%. It's a 30% to 45% difference. That's a much larger difference. So the baseline is important. You need to bear that in mind. The other thing to bear in mind is that when we get these two values, they're coming out, they're shown together. There's the odds ratio, exactly as we calculated. And there's the relative risk ratio. It's actually showing it as a separate row here for having angina at 1.538. So this is where they relate to each other. You should bear in mind that When the odds ratio and risk ratios here are quite different, generally speaking, these two numbers start to become much more similar to each other when the proportion of people with the condition occurs relatively rarely, i.e. when you get down below 10%. They're a lot more different when you get above 10%. And what about these values, these confidence interval values? Well, they simply say that, look, if you were to repeat the sample a number of times, you would expect to see the ratio maybe to vary between 2.4 to 2.9 in both groups here, or 1.4 to 1.59. The fact is that they're both positive. They're both above 1. So we're basically saying that, yeah, look, the risk is increased here. This is a statistically significant effect, and you could see that, of course, using a chi-square value as well. So the 95% confidence intervals provide an indication as to how much these values are likely to vary from one sample to the next. For both odds ratio and relative risk estimates, both of the intervals are positive, so it's likely that these increased effects, positive here meaning greater than 1, it's likely that these increased risk effect exists in the population. Okay, our last section, we're just going to look very briefly at performing survival analysis. So I'm just going to open up a data set here, open up yet another data set here. I've got a data set here, which looks at when pain medication starts to have an effect. Again, this is a data set that comes with SPSS as part of the sample. I'm going to get rid of the output here so we don't confuse ourselves. I'm just going to quickly walk you through survival analysis. So why survival analysis important? Well, it's actually a family of statistical procedures. There's actually 4 different statistical survival analysis procedures within SPSS. The one I'm going to show is one of the most common ones. And it's of interest where the outcome variable of interest is time until an event occurs. It's commonly employed where researchers are interested in modeling the effects of different treatments or conditions upon patient survival time. And for this reason, survival analysis is a key technique used to analyze the efficacy of pharmaceuticals in studies of disease prognosis. So you're going to see charts like this. Time to event, or TTE data is what's called. And they're comprised of two key variables, 2 key factors. One is an outcome status. Has this event occurred, yes or not? Usually, I think the clue is in the title of the event is usually death. Have this person died? Have they survived? And a variable showing how much elapsed time had occurred before the event, up until the event occurred or did not occur. It doesn't always have to be death. It can be things like readmission. It's used in insurance for things like, when someone makes a claim. And in our example here, it's actually for quite a good outcome. It's when a drug starts to take an effect, when a pain medication starts to have an effect. So that's our event. The one thing we have to talk about, though, is the concept of censored data. This is a really important concept. The fact is that it's unavoidable with time to event data. You're going to get certain data points which are called censored. And this refers to unknown circumstances where we, for example, don't know how long the patient survived or how much time elapsed before the event occurred. It's basically missing data. It's an added complication of the analysis, but it's one that's incorporated into the various calculations that estimate survival time. Here's an example. When we collect data or we grab data off a database or we conduct a study, it exists within a certain point in time. And when we collect data from people, it doesn't start from the year dot. It has a certain time window. And if you're really lucky, you've got all the information you require, where you know when the person entered the study and when the event occurred. So, how long before the event occurred? Maybe it's a drug that's been administered, and you're saying, okay, the drug was administered at 12 o'clock noon, and it took effect at 3 o'clock. So that's good. You know when it started. But a lot of times, you'll get situations where people just drop out of the study, or where you lose contact with them, or they just don't turn up again, and that's called a censored event. It's called right censored because it happens on the right side of the time dimension. Sometimes the event probably occurred at some point. They probably had something happen to them, but we don't know when because we couldn't leave the study running ad infinitum. We had to stop at some point and call a day on it. So that's another form of right censoring where it happened at some point in the future, but we don't know when. And here's a really common one. When did it start? If somebody turns up with a condition, and you say, okay, we're going to see what monitor this condition, see what happens to this person. Maybe they're going to pass away from it. How long have they had it for? You don't necessarily know. That's called left censored. You don't know when it started. And another type of censoring is, again, missing data. When did the event actually happen? If they're only going for a medical checkup, say once a year, they could have developed this condition at any point during that occasion. And if you're measuring it in months, then there is an unknown element to as to when they developed that particular condition. So censored data is an important part of survival analysis, something you should be aware of. Now, when I run a survival analysis here, what you're going to see is you're going to see three different types of output. You're going to see cumulative survival tables. That's a way for me to look up and say, well, what proportion are surviving on average, after 3 years, let's say. We're going to see group comparison tables. This is where we want to compare one group against another, maybe two different age groups, maybe a control versus a treatment, or maybe two different treatments. And we want to see whether or not the treatment affects survival. And lastly, we're going to see survival plots. This is a way for us to actually see how many people have survived over time. So these are the things we're going to see. We're going to run a technique called Kaplan-Meier, and we're running against a sample data set of only 200 rows of data. Each row represents a patient receiving anti-inflammatory medication for treating chronic arthritic pain. You can get this data set from the SPSS samples folder, so where SPSS is installed. The time to event data is the time before the medication actually has an effect, if it has an effect at all. And the event data simply denotes whether the effect occurred or whether it didn't occur for that person. The key additional variable measures whether the treatment was administered with a new drug or using the standard medication. And the file is called painmedication.sav. This is how I'm going to set up the Kaplan-Meier. I'm going to define the variable time to effect as my time variable. The variable status is whether or not the pain medication actually kicked in. And the factor field here is whether or not they were using the standard treatment or the new drug. And then I'm also going to ask it to give me 3 different statistical tests. And I'm going to ask it for a bunch of charts. Okay, so let me go and set that up. I'm going to go here to analyze, down to survival, down to Kaplan-Meier. Look, there's lots of different statistical survival analysis things here. Kaplan-Meier is commonly used. Time is time to effect. The status variable is this effect here, status. And I'm going to say status is 1, means it takes an effect. If I can't remember, I can right click and see 1 is taken effect here. That means taken effect. And treatment is my factor here. I've got treatment variable here. 0 new drug, 1 existing drug. They can be coded whatever way you want. If I go into compare factors, I'm going to ask for all 3 different types of test here. If I go to options, I'm going to ask for a bunch of different charts and output here. Click continue, click OK. And it produces this result for me. So the first thing I get is a survival table, 1 for the new drug. And if I scroll down through that, this is a survival table, tell me the proportion still surviving. Then 1 for the existing drug. And then I get some descriptives telling me the average survival time for one drug versus the other drug, some significance tests, and some charts. Let's just take a moment here to look at this in a bit more detail. So here is my survival table. I'm just showing you the top of the table. Let's just walk through this. The first is simply saying what part of the table is it? This is referring to the new drug. So all of these statistics refer to the new drug, not the existing drug. There'll be another table below that referring to the existing drug. Time to effect is how, I don't know how it's measured. I don't know how, it doesn't tell me. I'm going to guess it's hours. So 0.6 hours is about 36 minutes, feels about right. So 36 minutes before it takes an effect. And then the status note says censored cases are not included in the calculations. You'll see censored cases, but obviously you can't include them in the calculation because you don't know when it had an effect. It didn't have an effect. Or what I suspect is happening is that the patient is saying, look, this isn't working for me. Can I have something else? And therefore they're taken out of the calculation, taken out of the analysis. We don't know when the effect, if ever, would have occurred. And then we have the cumulative survival. This is just counting things up over time. So we're looking at over time. So the proportion of non-censored cases where the effect has not occurred yet. So at 0.9 hours in, 95% of the cases have not, 95% of the patients, the effect has not occurred yet. Standard error is just simply a measure of variation of how reliable a statistic is. It gets larger, means the error gets larger as you run out of cases, because as you're going down through it, you're taking more and more cases out of it. You can see here that we had, two cases where it occurred at 0.36, and then a case that occurred at 0.7, then a case that occurred at 0.8, and then another case that occurred at 0.9, leaving 99 cases still on the 99 patients still receiving the new drug. And then we have the cumulative event and the count of events thus far occurring. 1, 2, 3, 4. So 5 patients thus far, it's kicked in. And then we have the number of non-censored cases remaining where the effect has not occurred. As I say, this is how many cases how many patients who are still waiting for the drug to have an effect on them. So that's how we read the survival table. It's not that difficult. It's mostly proportions. What we also have some other output here. We have means and medians. So I'll just show you the means table here is just saying, look, the average time it takes before the new drug kicks in is 0.48 hours. For the existing drug, it's 0.51 hours. It's not a big difference. The 95% confidence intervals for these two groups actually overlap with one another. So they're probably not statistically different from one another. We can guess from that, it looks like it could be as high as 5.5 or it could be as low as 4.4 for the existing drug. The same for the median value here. The median time that it takes, the 50th percentile, is 3.7 hours for the new drug and 4.1 hours for the existing drug. The percentiles simply say that at 7.1 hours, 25% of the new 25% of the patients in the new drug still haven't had an effect. At 7.7 hours for the existing drug, 25% have not had an effect. The 50th percentile is exactly the same as the median values, and the 75th percentile simply says that, at 1.9 hours, 75% of the patients still hadn't had an effect for them using the new drug, and at 2.4 hours, 75% of the patients still had an effect for them using the existing drugs. And then we have our 3 tests. All of the 3 tests are showing that, looking at the survival distributions, that there's no statistically difference between these two drugs. It doesn't look like the new drug's necessarily better than the existing drug, or the existing drug's necessarily better than the new drug. I've got some information here about the differences between these different tests. They're trying to dealing with different problems. There's no universal test. Log ranks means all time points are weighted equally in the test. Breslow tends to weight the earlier time points where you've got more cases, more in the test, and Tyrone-Ware tends to use a compromise of both of them. So Tyrone-Ware is a kind of standard one to use. Suffice to say that the significant values are all above 0.05. So there's no statistically difference between these. And if we look at survival function chart here, here's the new drug, which is the blue. Here's the existing drug, which is the red. It does look like the new drug kicks in a wee bit earlier. We can see that we're running out of cases here. These plus signs are censored cases. These are cases where the patient has basically been taken out of the study because they've probably said, look, I'm in agony here. I need to have something. Can you give me something? The 1- survival is the opposite of that. It's just the opposite of that. It's just the inverse of that. It's just saying at 8 hours, how many cases has it had an effect on? Looks had an effect on about 80% of the cases at that point. The survival function denotes the probability that a person or subject will survive beyond a given time point based on the rate of occurrence of sample data. But the hazard function denotes the rate or failure of non-surviving or occurring at the given time point based on the fact that the subjects have made it this far without encountering the event of interest. The key here is the cumulative hazard, and I wanted to just really point this out. It's quite confusing for a lot of people. The cumulative hazard measures the expected rate of occurrence. It's not the proportion, it's the rate of occurrence in a given time point. So the values can exceed 1. If the periodicity was measured in years, for example, one could reach a time point where a given event might be occurring 1.5 times a year on average by that stage, or alternatively 3 times every 2 years if it helps you. It's like saying, how many times would you expect the event to occur if it could happen repeatedly, if it could happen more than once in a given time period? And therefore, the cumulative hazard looks like this. It's showing, by this stage, you'd expect to have the event occurring 2.5 times by this stage. So it's a very important way in which analysts measure risk over time of a hazard occurring. And it's different from the standard survival charts because it's not using a proportion, it's using the number of times something would occur. So very different, rather like the difference between relative risk ratio and the difference between odds ratio, or odds ratio looks at number of times you're more likely to have an effect occur. Okay, lastly, I just wanted to point out to you the fact that when you get this PDF of these slides out, these links will take you to videos that look at these topics in more detail, slightly slowed down detail. We try to cram a lot into this session. So if there's something here that you're particularly interested in, you can see a video that looks at this in more detail and goes through it a little bit slower. Bear in mind that we can help you with transforming and analyzing your data, and we offer self-paced, virtual, and in-person training courses on how to use SPSS products and appropriate statistical methods. We also offer a mix of consultancy and training, whereby we do the initial work and then teach you how to replicate it. And we also help with sourcing your SPSS software. We provide, as I say, formal classroom training, virtual training, online training, and we provide formal technical support around SPSS to our customers. But generally speaking, we provide no strings attached technical and business advice related to analytics to anybody that comes and approaches us. So do feel free to reach out, even if you're not a current customer of Smart Vision. In the meantime, I hope you found that useful. We do run webinars on a regular basis. If you look at our forthcoming schedule, you'll see what other topics we're covering in the near future. Thanks for sticking with it, and we look forward to speaking to you again in the near future. Thanks very much.